Mahesh will be talking to us about learning-based approaches in multi-radio mesh networks. So with that, I'll hand it off to you.
Thank you so much. Um, so this is a joint work with a PhD student of mine, Sophia, who just presented this paper at ICMP, and Philip, an undergraduate who worked with us on this project. So before I talk about the talk, I thought I'll just remind for the geographically challenged where Edinburgh is. So in terms of, this is Britain in the world, and this is where Edinburgh is. And a lot of you probably know Scotland for whiskey or some such other thing, but there is a symbol of Edinburgh which is really gorgeous, which gets people every year, especially during August for the festival period. So quite a popular time to visit Edinburgh. So if you're thinking, then I think they should probably tempt you to visit something. And we are in a new building where about 500 researchers, quite a large department working on a range of things. We're growing in the systems area. Hopefully there'll be faculty positions coming up in the coming years. So you can look out for that as well. So with that, let me get back to the topic of my talk today. So most of you may be familiar with the concept of wireless mesh networks in terms of having a multi-hop extension to the traditional wireless LAN that we're aware of. So that's, in very simple terms, the concept of wireless mesh networks. In a mesh network, you have routers, which are also serving as access points, and these routers communicate in a multi-hop wireless fashion to provide internet connectivity. You may have some gateways which are directly connected to the wired internet, and the clients sort of use the network as if it is a typical Wi-Fi network. And the number of advantages of wireless mesh networking, the primary advantage is cost, because the wires in the Wi-Fi deployments are quite expensive. Because of that, there is a lot of effort that's put into trying to optimize the locations for the access points, and all of these can be avoided if you just densely deploy wireless routers forming, self-organizing into a mesh network. Also, you have, because of the mesh connectivity, you also have improved coverage and robustness. Given the advantages, there have been a number of application scenarios for mesh networks or multi-hop wireless networks in general. And the most compelling application scenario is that of citywide public wireless access networks. So that is something that's becoming more and more common, and I'm going to mention that again later on. All that is, all these positive things are great, but from a technical standpoint, the main issue is that the capacity is scaling. As the network size increases, you have larger number of hops to communicate your data, and combine that with the fact that the underlying wireless medium has to be shared, and these two together present fundamental limitations in terms of how much we can get in terms of end user throughput. So these have prompted people to look at not only the limitations or fundamental limitations of how much capacity one has in a network like this, but also ways to improve the utilization of these networks. So one such way of doing it is using multi-radio wireless architecture, where instead of having a single radio set up, we have multiple radios which can operate on multiple different channels, and these can form the high-capacity backhaul. Okay, so this helps in mitigating the performance degradation that I sort of alluded to in the previous slide. But also, if one has access to a larger amount of spectrum, potentially one could more efficiently use this in a dynamic form using this multi-radio architecture. So it's very practical architecture, widely considered to
So
be.
what's the typical range of those routers? For example, how far can they reach?
Depends on whether it is an indoor and or outdoor scenario, but typically if you're using omnidirectional antennas, it could be indoors, it could be in the order of several, few tens of meters.
Outdoors?
Outdoors, it could be few hundreds of meters. It all depends on the types of the antennas. So if it is a very high gain antenna, or if it is a very directional antenna, you could get up to several tens of kilometers. So we have another project where we are looking at rural broadband and the use of long distance Wi-Fi. So in those scenarios, you could get tens of kilometers. It's very context specific. But here we are assuming more densely populated areas where you typically use omnidirectional antennas in a city setting. So the multi-radio architecture is something which simplifies protocol design to an extent. Yes.
Why do you use iteratively as a wireless backbone?
That is something that people are doing. So basically, part of the reason is because there are more channels that are available in the 5 gigahertz band. And most of the client devices tend to support the 802.11p or G standards. So the trend in terms of mesh networking products is that you use 802.11a for the backhaul and B or G for the access network. So essentially you have a two-tiered architecture where this separation in bands happens. Okay. And in this, essentially you have an access interface which allows you to connect to the clients from each of these routers, and you have mesh interfaces which are primarily for backhaul communication. Okay. So the problem in this setting is how do you assign channels to these different interfaces? Okay. So this problem has been looked at from a theoretical standpoint by some people, and it turns out that it's a very hard problem, especially the typical case where the number of interfaces are smaller than the number of channels, which is quite common. So in the 802.11a context, you have up to 24 channels, whereas it's not possible for size and practicality to have that many number of interfaces. So this is a hard problem even if you're aiming to solve this in a centralized setting. Okay. It becomes even more harder if you aim to do that in a distributed setting. Now, a natural question to ask is it necessary to solve this in a distributed setting? Okay. The answer to that is it is becoming necessary, partly because of several things that happen. Most important being that large-scale deployments are increasing. So as you can see, there are several citywide public access networks coming up, especially in small places like Madison or in Mountain View. There are networks in the size of about a few hundred mesh routers. Okay. And Taipei is an extreme example in the sense that they were aiming to deploy about 10,000 mesh access points to blanket the whole of Taipei. Okay. So when you have a very large scale network, it is very natural to consider a distributed solution because if, and especially in a dynamic context where the interference characteristics in different spatial locations could be very different. So that necessitates a very localized approach to channel allocation. And precisely because of the combination of these reasons, one requires a scalable and adaptive distributed multi-radio allocation protocols, as opposed to the centralized things that many people have looked at in the past. So like I already mentioned, the distributed problem is difficult. The key reason is because of something called the channel dependency among nodes. So in simple terms, essentially the problem is that if a particular node allocates a channel to one of its interfaces, that could cause an effect which actually can in the worst case, affect and cause a ripple effect of changes across the whole network. Okay, so in a way, to contain this channel dependency, a lot of people have made a lot of simplifying assumptions. I'll point out the current state of the art in this problem, and again reiterate our particular design goals in looking at this problem. So the existing work, there's a significant amount of work in this area in the past few years. Broadly, it can be classified into two categories. One is a category where a particular role is assigned to an interface. It could be as a parent interface or a child interface when you have a tree type of a structure that is imposed on the network. Or it could be as a sending interface or a receiving interface when you sort of use interfaces in that form. And the other category of protocols essentially have some kind of distributed mutual exclusion happening. So basically, you have a particular node trying to get a lock and make a change. And after that change has happened, then the other nodes around it will try to get a lock, and then they try to make a change to their interface allocation and so forth. So this, as you can imagine, when you try to negotiate among multiple nodes to make each and every interface channel allocation, there could be a significant amount of overhead. So one could enumerate the limitations of each of these existing pieces of work, but broadly speaking, these are the list of limitations. So essentially, restrictions on interface use also sometimes comes with a restriction on the traffic patterns that can be efficiently supported. And like I said, negotiation-based protocols are associated with higher overhead. And many of these proposals also assume that a common channel is used for negotiation. And that also is another source of inefficiency. And pretty much all the existing work does not consider this notion of adapting to variable interference characteristics in different parts of the network. Okay. So these are the reasons.
So interfaces, do they work on the same band, or for example, let's say the two interfaces you're talking about are between 11A and G,
right?
Or like P and G.
Right.
So does it also interfere in the bands?
Do you mean whether we use interfaces within a single band?
No, for example, they are.
I think the question is, what exactly does it mean by an interface?
Yeah. So
That's, I think, what.
It's a network interface card. So basically,
can you give us examples.
So an 11A radio, it's on a card or on a chip in your PC, that's an interface.
yes.
But an 11A, and somehow it's not 11A on this channel is one interface, and 11A on some other channel is a different interface.
That's a different interface. So here,
So
if you
11A
have
on
the
two
physical
different
interface,
channels.
sorry?
So within one, say one access point, one of these forwarding devices, 11A transmitting through one channel is a different interface than 11A transmitting through another channel.
Exactly. Yeah.
Wireless cards.
So you view that, but you're requiring that essentially two radios in the laptop, one for each channel.
Yeah, not on the laptop. This is for
Well, like in some
Right.
forwarding.
right. Yeah.
So is your model of these forwarding devices that they have a lot of radios or several radios?
Yes. So I can show a picture later on. So basically, these embedded boards that you get, which are typically part of these mesh routers that Tropos or Cisco or all these companies put together, essentially they have slots for multiple different radio cards. Okay, so basically each of them could be tuned to a different channel, and essentially those are the interfaces that we are trying to deal with. So basically, though we are trying to determine the channel allocation for those different sets.
What about one radio that time shares between two different channels? Are you excluding that sort of from
Yes,
your
we are excluding that partly because it makes
Makes it complicated.
it creates the requirement of time sync and all that, especially in the multi-hop wireless setting. So people have looked at multi-channel MAC protocols, but what we are looking at is slightly above that, where it happens on a relatively smaller, longer time scale, where you look at channel allocation for these interfaces separately. So you
Okay,
have,
I get it.
okay. So, any other questions? Okay. So these are the various set of limitations from past work which motivated us to look at this problem, and our primary goal was to come up with something which is practical. But besides that, we also have several other goals in terms of trying to address the limitations of past work. The first is efficient channel utilization. This is sort of expected and something which one can appreciate. So essentially the goal is to spread the amount of contention among as many channels as possible, so that on any given channel, the amount of interference is reduced, and that leads to efficient spectrum utilization. And the scalability aspect has to do with trying to reduce the communication overhead for the channel allocation process, so that if you were to do it often to adapt to various things, you're not going to overwhelm the network with overhead. And the adaptivity aspect is in terms of the ability to trying to come up to a reasonable channel allocation if a change happens in the network. It could be a failure of one of these devices, or it could be that in a particular portion of the network there is significant interference from a co-located wireless network, and you need to reallocate your channels. So how fast you do that, and the resulting channel allocation, whether it is acceptable. And flexibility has to do with several things. The important aspect of flexibility is trying to support a wide variety of traffic patterns. So this becomes important when you have a larger network, especially. So if you have a citywide network, the percentage of traffic that goes between these peers in the network increases. Okay. So if you have a room-wide network, the very likely case is that you would be talking to people who might be on the internet somewhere. Okay. So flexibility is supporting arbitrary traffic patterns, working on any routing protocol, not restricting the use of an interface, and things like that. So our approach to addressing this problem is learning-based. By that, I mean two things. One is in terms of how nodes come up with their channel allocation. Okay. Each node in our framework autonomously comes up with its own channel allocation for the interfaces on a node. And this is done based on local information that is gathered via a accompanying neighbor discovery protocol. So the local neighborhood information and also the channel utilization map is gathered using that. And that is the second component. So basically, the neighbor discovery enables this autonomous learning of channel allocations. And because you learn, each node learns these channel allocations in a pretty much independent way, this is sort of a learning-based approach. And it is fundamentally different from the existing approaches like what I've presented before. Now, in terms of the main parameter that we are trying to tune, we call that a channel set. So for each node, we have to determine a set of channels that are of the size equal to the number of interfaces on that node, and that is referred to as a channel set. So here's an example. So suppose if you have 3 channels and 2 interfaces, so the number of combinations of 3 channels to 2 interfaces is 3. So we need to pick between one of these sets, and each of these this is the set of all possible channel sets that we're working with. Of course, if you have larger number of channels, you would have more combinations. Similarly, it's sort of a combinatorial thing.
So the number of channels can be, I thought number of channels can be same as number of interfaces because how...
That is a trivial problem. So basically, that is not a realistic case.
What is the channel then? How is it different from an interface?
The channel, like I said, in a 5 gigahertz context, you have about 24 channels. But on a typical multi-radio platform, you have up to 3 interfaces available for backhaul communication. So what that means is you have to pick 3 channels out of 24 to allocate to the interfaces on a node. Okay. So that's the main tuning parameter. So each node has to determine a good channel set. In terms of the conceptual architecture, so this is where the ALCAP protocol sits. It's at the link layer. So you have a number of mesh interfaces, and you have an access interface as per the 2-tier architecture that I mentioned earlier. And you have the routing and IP forwarding that's happening as usual in the IP stack. Okay. So the important thing to notice in this picture is that the neighbor discovery component is the only component that is interacting with the network. Okay. So the channel set adaptation is pretty much local and it is sitting at every node. It is just depending on information that is gathered by the neighbor discovery component. Yes.
Are you saying that each node independently picks its allocation?
Yes.
He's not really saying that though, because when one node picks its set, right, you'll do this neighbor discovery thing to listen to what they're listening to.
Yeah, and then you sort of learn over time what...
You'll change what you listen to or transmit on
So
based
there's a
on
temporal
what
aspect to it, is what you're saying.
There's a dependency among the choices neighbors make.
I understand
Yes.
that.
Is that right?
Isn't that
Yes.
a bit dangerous in that you might end up changing things constantly or in terms of stabilities?
Yes.
That's why he can write papers about it. You can do bad stuff that doesn't work. Is that right?
Yeah, I mean, I think stability is an important issue I'll touch upon later on, but yeah, that's a potential danger, yeah. So, but the attractive thing is that, independently you're making these decisions purely based on what the neighbor discovery gets you, and then neighbor discovery also gets the channel utilization information at every point in time. And also the neighbor discovery can sort of reduce the duplication of work that is done by the routing protocol. For instance, if the routing protocol has hello messages for its purposes, that could be taken over by the neighbor discovery component of this LCAP. Okay. So neighbor discovery, is that a big deal? So that's the question to ask, because I listed that as a crucial component that enables our channel allocation protocol. The answer is that it is when you let nodes independently choose their channel allocations. You could pick channels such that your neighboring nodes may not have a common channel with you. That pretty much makes the communication between them impossible, so you do not know what the other nodes are doing. So it's important to know what others are doing for you to pick a better channel set in the next iteration. So this is sort of illustrated in this picture where 2 nodes choose completely disjoint set of channels. Okay. Now, a naive solution to address this is let one of these mesh interfaces cycle through the unused set of channels. Suppose in this picture, you have a total of 4 channels. 2 channels are used by one node and the other 2 channels are used by the other node. So this particular node is not using 2 channels in the overall set. So it could have one of its interfaces cycle through the channels 2 and 3 and send hello messages on. And that could allow announcement of the presence of this node A to node B, and vice versa. You could do that. So in our context, this could be potentially disruptive to the channel allocation process. Okay, so you're doing channel allocation, You're using neighbor discovery to assist in channel allocation, but then neighbor discovery itself could hurt channel allocation because it could pretty much slow down the channel allocation process and make things even more inconsistent because we're looking at a distributed setting.
Okay.
Yes.
So in the slide, does neighbor refer to another mesh router that you link to, or just another router that you can overhear?
You could have a communication link. I mean, I think
In which case you would need to share at least one interface on the same channel.
Yeah, exactly.
But in this example, I guess they're not.
They are within the, so in terms of physically, they are able to have a communication link provided they have a common channel. So in this example, they do not have that communication link because they're using different channels. Okay.
But an interface, when you said that an interface will run through other channels, it can potentially go to other channel and he'll listen to it. Right? Basically, what if those two interfaces cannot even use those other channels, so they will never interfere. They can never be neighbors. Right?
I'm not sure if I completely understood your question, but
Okay, so what I'm saying is, let's say the two interface A cannot even work in channel which interface B has.
okay.
So in that case, they can never be neighbors.
Yeah, they cannot. I mean, I think there is some fundamental reason why they cannot use a certain channel. Of course, they cannot communicate. But in practice, you could use any channel on any given interface. It's sort of a configuration thing. So that's basically suggests that you could, in principle, enable a communication link by just switching your channel to your neighbor's channels.
You're only considering orthogonal channels, like on 11G, right? They define a lot of channels that overlap, but you're excluding those kinds of channels.
Not necessarily. So I think you could have overlapping channels as well. What we're looking at is slightly at a higher level. I think, of course, you have the interference that comes from potentially overlapping channels, and that needs to be taken into account in terms of how you define the channel set. So, okay.
So what happens if there are only few sets of channels which are common between you and your neighbor? So
What?
For example, A can work on 1, 2 and B can work on 1 and 3 only. So there's only partial sets of channels which are actually overlapping between your node and the neighbor.
That's fine. Actually, that makes neighbor discovery a non-issue. If you have some overlap in terms of the channels that two neighboring nodes are using, then it's a non-issue. But my thesis here is that if you have many channels but very few interfaces, the likelihood that two neighboring nodes might choose completely disjoint set of channels is high. That necessitates that we do something about it. Otherwise, they cannot discover each other. They do not know what the channel allocation is on those channels used by neighbors. So our idea is to, in a way, cheat. Okay. So the idea is to use the access interface. So like I said, the two-tier architecture is fairly common, and you have this access interface that you use normally to communicate with clients. And what we are doing is we use the access interface to sort of go and do that job for us, instead of having one of your mesh interfaces do that. Okay. So essentially, same picture as before. So imagine that here there is an access interface which is actually being used for the client communication, shown in orange here. So what we're going to do is we're going to sort of use that access interface to send hello messages on these two channels to announce the presence to node B. So, okay. And so that is how you announce and let your neighbors know about your presence. Now, this is quite possible and very practical in today's scenario, but how you do this is the question. Now,
So it could be some third interface, right? It doesn't have to be the access interface. You're just saying that.
yeah, it could be third interface, but then
One of
if
the
you are
two.
purely using it for this intermittent activity, that is a wastage of resources. So
No,
you
but-
already have this.
But you could use one of the two interfaces you have for a little bit of time. You could use, say, interface 3 to do this kind of roping, or talking to people who are not in the same channel as you were before you started probing other channels. I don't see, like, if I have a large number of interfaces, then I can do many things. But yeah. The
Yes.
idea is that is there a specific reason why you're using the access interface? Or
Because it is there anyway, and then the client communication is dependent on you having a channel assignment in the backhaul. So it is okay to suspend activity on the client interface to use it for assisting channel allocation in the backhaul. So that is the reasoning. Now, if you have many interfaces, this problem becomes trivial. So, but the usual scenario is that you have few interfaces, you need to judiciously use them and try to get a channel allocation quickly.
Okay, so
I'm assuming that all the access interfaces are on the same channel,
right.
or different channels.
No, there could be a different band altogether. So typically what you have is you have 2.4 gigahertz on the access interface and 5 gigahertz. But the underlying assumption here,
Gigahertz on the back end.
yes.
I'm wondering if you have your access point A and B in the example. Is the access interface from access point A on the same channel as the access interface from access point B?
No, not necessarily. Yeah, I think maybe this choice of color is probably misleading. So you could have completely different. In normal deployments, two neighboring access points would typically be tuned to different channels.
Maybe I don't fully understand your proposal yet. In this case, I think you're saying that you use the access interface to communicate which channel you're on. If access interface from access point B is on a different channel, how would it?
No, it is not. The communication is not between access interfaces. The communication is between access interface on this particular access point and the mesh interfaces on these. So because you are trying to send a hello message on channel 2 and channel 3 using your access interface, your neighbors can recognize your presence.
Oh, so the access interface might be on the same channel as some of the backend interfaces.
Exactly. That is the idea.
And
And-
that's the first thing you precluded, right? Was this idea that, like you're thinking of the backbone interfaces as being 11A, 5 gigahertz, and because the access interfaces can be 11B and G.
Sure. But I think basically in today's times it is much cheaper to, or it's about the same or cheaper to just get a multi-band interface. Anyway, this is the access point which is in the control of the infrastructure that you're trying to design. So our underlying assumption here is that these access interfaces are multi-band capable. We are not saying anything against the typical deployment model, where people use B or G for accessing as an end user client. That still holds here. Okay.
So you use this access interface, but you tune it to some other band that isn't used by the mobile terminals for access. Into some channel, is that?
Yes. So basically, essentially, let's take a concrete example.
Yeah.
Okay.
And maybe you should, if you go forward, we'll.
Is that a
I think-
channel everybody knows which channel it is?
So imagine that you're using channel 6 for the access interface. Okay, channel 6 on 2.4 gigahertz. Okay, which is in 2.4 gigahertz, which the users
An
connect.
A or a B or both?
Just B.
No.
At node A. Okay, and these channels 0 and 1 are in 5 gigahertz. Okay, so imagine that you have 4 channels in 5 gigahertz. So what I'm doing here is the access interface now switches a band, And then, since it is not using channels 2 and 3 for its mesh interfaces, it is going to tune to those channels and send a hello message. Okay, so basically it sends a hello message on channel 2, which is heard by this node because it already has a mesh interface tuned to that, and then it does it for 3. And so basically you may have not just one neighbor but a number of neighbors where your goal is to send a hello message on all of the channels which are unused by your own mesh interfaces. Okay, yes.
Okay, so the motivation for using the access interface was the reason you are not using the mesh interface is because you don't want to use the bandwidth which is there of the mesh interface, right?
And also you do not want to disrupt the channel allocation process. Because if you sort of disturb the existing mesh interfaces to sort of do this neighbor discovery, then you are in a way, at least in our framework, this is going to be disruptive. Because you are letting nodes independently do this channel allocation.
No, you are not allocating it, you are just okay. But the question is that even in this scheme that you are talking about, when A is informing B about 0 or 1 or 2 or 3, whatever, at least it's eating the bandwidth of B, right? It's not eating the bandwidth of A, but at least it's eating the bandwidth of B because.
Why would it be eating?
Because the access interface is tuning into the same frequency.
Yeah. So for sending that hello packet, yes.
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 So then basically you can say that okay, nothing at A is getting used, and because we don't want to disrupt the data communication which is going at A, but the data communication at B is interrupted, or all the neighbors is interrupted. So I'm not sure, how strong is this motivation of using the access. You could have actually used the mesh interface as well. So, so that's.
Yeah, I mean, I think in some ways one could probably make an argument that you're anyway using part of the bandwidth on the channels for neighboring nodes. Fine, but in our context, I think the rationale was this access interface would be unused anyway because it has to depend on the backhaul channel allocation to converge and to be available. So during that period, it is okay to suspend activity on that. And then sort of create a temporary interface that you can use for this purpose. So that was the idea. Okay.
I think you
So
can.
sorry.
Go ahead.
So there's another argument. If you keep switching your data interface channel to send the hello messages, then you won't be able to receive those hello messages yourself. So if you had 0 and 1 in node A, 0 switches to 2 to send a message. Somebody else is sending a message on channel 0. And
Yeah, you would
miss
not be
it.
able to receive. Yeah.
So that's why it's better to use the access
Yeah.
interface.
Thanks for helping me out. So
Yeah.
basically, so many
You
questions.
just need one mesh interface. You don't need all of them.
Well, so you lose one interface anyways, right? You have
So-
nobody listening at 0, and you are supposed to be listening at 0 at default.
I think it also depends on how frequently you are sending the hello messages. Like,
Yeah,
What's
so
the
basically,
bandwidth?
it is.
When you switch sequence,
Yeah, it is adaptive to the state of the channel allocation process. So basically, in our method, it is dependent on how much of your channel allocation process is complete. So if you're completely starting from a random channel allocation state, you would send them frequently. So there will be more overhead during that. So in terms of enabling this usage, you need to be able to suspend client activity for a given period. And this can be done in a straightforward way if your access interface uses 5 gigahertz. But more often you use 2.4 gigahertz for your access interface. And for that, we have a very simple technique called nav-based channel quieting, which is basically using the network allocation vector feature of 8.11. And this is already done for other purposes in 8.11, such as if you have .11b devices and .11g devices, so you use this feature for .11g protection. And that's one example, but there are several other examples where this kind of feature is already used. So the idea is that whenever the access point needs to quiet a particular set of clients, then it is going to generate a gratuitous control frame, CTS frame, addressed to itself, with the duration field set to the time that you want the channel to be quiet. So essentially, during that period, because these stations respect the .11 protocol, they will not initiate any communication during that period. Okay, and then once that period is over, everything is back to normal. So this sort of a technique, this technique is has several advantages. One, it is compliant with the .11 standard. It doesn't require any client-side modifications, and importantly, you do not have any synchronization between different nodes. So basically, everyone is doing this independently. Okay, so it's a very asynchronous kind of thing. So we have implemented this in our test bed. This component. The main challenging part was when you're trying to switch to the different band and different channels to do neighbor discovery, you run the risk of dissociating with all the clients who are associated with you. Okay, so that's what typically happens when you switch from AP mode to the monitor mode we are using for neighbor discovery. So what we have done is we use the virtual interface feature that's already there. So you have two virtual interfaces doing these two different tasks. And sort of this picture essentially sort of illustrates that the channel quieting feature is working. So the gaps between these lines essentially are the gaps between the times that you generate this quieting packet. Okay, so you have two nodes which are trying to communicate, and you have a third node which is trying to quiet the channel. And essentially the height of these peaks is about 32 milliseconds, which is basically the quieting period we used in this experiment. And sort of this happens in a very reliable way.
So if, one quieting period you scan all the channels, or do you like scan one channel then go back to normal operation and then again after some time scan another channel and so on?
Good question. So it depends on the amount of time you need to do this band switches.
Because 30 milliseconds looks like a long period of time, right? Or isn't it like people do, won't your access network feel anything for 30 milliseconds, then it will be fine?
Yeah, I mean, I think it is comparable to sort of beacon transmissions and some of the overhead in terms of management traffic that happens every 100 milliseconds. So, but in 30 milliseconds, you could switch between different channels and send other messages.
So you quiet only your neighbor, all the neighbors around you, or what?
No,
What
you quiet the clients associated with the AP. Okay, so you do not quiet your neighbors. Okay, any more questions? So as a whole, this is one of the modules we have. So you have hello messages happening as usual on mesh interfaces, but also we are using access interface for other unused channels. And this is the information carried, broadly speaking, by these hello messages. And these are stored in a table at each node. Now, let's go to the other component, which is the channel set adaptation component. So what we are doing essentially is sort of a probabilistic trial and error thing in a way. So basically we are trying to learn over time in terms of what a good channel allocation for you is. And in order to do that, we use this the framework of learning automata. So essentially the learning automata are intended for use in very uncertain environments to do adaptive decision making. So the idea is, so one could look at it as doing a series of experiments and then arriving with the right, and eventually ending up with the right configuration. So the problems, the fundamental problems that make this problem difficult are these two. different nodes may have inconsistent and different views of the channel allocation in this particular case, and then they could be making mutually conflicting decisions. So that sort of relates to the question that you were asking in terms of this can happen forever. It may never converge. So that is the potential danger. So we have sort of seen that in our scenarios, you would see convergence. Okay, but there is also theory which suggests that under certain conditions these things do converge. Okay. So essentially, what you do, you associate a probability vector with each channel set. So, like I said initially, you have various possible channel sets. You have to pick one of them, and you have a probability vector with a probability for each channel set. You start off by having all of them being equal and summing up to 1. So which means you could use any channel set. And over time, you try to reinforce some at the expense of others.
So that S, like PS, is the number of different
Number of different channel sets, exactly.
Mapped to your interfaces.
So these
In
are
your example of like two interfaces
and 3 channels.
Sets, it was,
Right. So basically, if you know,
that's the S you're talking about.
yeah, exactly, yeah. Yeah. So basically, once you know what channels you have to use, you can assign in any form to your physical interfaces, because you have just the same number of channels as the number of interfaces you have. Okay. And so this we use a standard reinforcement scheme called linear reward penalty. So essentially what this means is that if you're using a current channel set, if you have a channel set that you're using at the moment, you try to evaluate how well it is doing when you're about to make this adaptation. So if it is still the best channel set, then you're going to reinforce it further by rewarding it. If it is no longer the best, then you're going to penalize it and benefit everyone by giving a fraction of the reward compared to the penalty you're giving to the current channel set. Okay, so that's basically what is happening in these equations. Okay, so
So why do we use this linear like reward penalty? So look at the difference between the two lines. Say the mean equals below that. So the difference between these two values, if expanded, is just real constant, right? A, right? So if I belongs to say S, you give that value, otherwise you say each another. So you look at the difference. That's the constant A.
can you speak a bit louder? So
Okay, so my first in general is why you
why linear?
Yeah.
Yeah. So basically, linear is because it's simple. I mean, I think there's that's the short answer to that. That there are non-linear schemes as well. And I think if you look at learning augmented literature, there's a whole body of work looking at various reinforcement schemes. So linear is something that is widely used for practical applications. So therefore, we start off with that, and then it seemed to work reasonably fine. But one could actually investigate within this how much going to a non-linear, more complex scheme would benefit you. Okay, that's a topic for future work.
and you say A and B are learning parameters.
Right.
So do you need a long training period to optimize some metric, and from that one you solve for A and B?
No. So basically, these parameters, there are different ways to obtain these parameters. One is that you sort of choose them arbitrarily, or you can sort of experimentally obtain them. You don't need a separate learning process to learn these parameters. So these are just parameters which actually determine the weights for the reward and the penalty. So these are constant values. Okay. So one could refer to the literature to obtain what might be good numbers. In our case, what we have done is we've sort of experimentally looked at what parameters are giving you most benefit, and then we use those parameters in our setting.
What's the benefit is defined as? There is some systematic benefit. You tries to boil down to a single objective function.
So in terms of I'll have to. I don't recall the exact conclusion we had on this learning parameters in terms of how we sort of ended up choosing the specific values for that at this moment. But I can probably follow up and let you know the specific criteria we use, because this was something that we had to choose, and then we did not spend as much energy in that particular segment. Okay. Yes.
So I missed this. So how do you determine whether something is good?
Yeah. So basically, I will come to that. Yeah. So. So I said you have to pick, determine whether a particular channel set is good or not. So that for that we have a metric called channel set quality metric, and this metric sort of loosely reflects the delay you experience by using a particular channel set to communicate with your neighbors. Okay, and I haven't put the equations. The paper has all these details. So essentially, the intuition is that if you cannot communicate with a neighbor over a channel, then the cost of using that channel to that neighbor is infinity. Otherwise, it would be based on the utilization in the neighborhoods of both the sender and the receiver. Okay, so basically, if the channel is heavily used, both in the neighborhood of the sender and the receiver, then the cost is going to be greater. Okay. And you do this for each channel and each neighbor, and overall you determine the cost for your channel set across all your neighbors. So that is the aggregate cost we use to determine whether a channel set, determine the cost for a channel set. Okay.
It's like for
So you were transmitting a particular channel set, right? And now you can evaluate these delays you experience communicating with your neighbors, right?
We are not measuring the delay per se. We are measuring the number of interfaces in the neighborhood which are using that channel. So basically, this is a channel utilization. It is not traffic dependent.
Okay, all right. How do you evaluate the cost of other channel sets to compare to?
Because you are getting these neighbor discovery messages which tell you the channel utilization for each interface.
For each possible, so you're saying that somehow, before you update your probability vector, you get a number associated with each channel, which is somehow its usage
Right.
or it's the load
Exactly,
on the
exactly. You get that through the neighbor discovery, and then you factor that in trying to compute this cost for each channel, each possible channel set, including the one that you're currently using.
And the good channels are the channels that are
Least used.
least used. But a channel that's least used is one that nobody's using.
Yeah, but you have this connectivity constraint, which is basically it is going to set the cost to infinity if you cannot communicate with a neighbor on a channel. So basically that sort of accounts for the fact that you want to be connected with all your neighbors.
Suppose you got started a system in a state where everyone listened to, everyone had 3 interfaces and everyone tuned to channels 1, 2, and 3.
Right.
How do you break out of that trap to explore channel 4?
Right, that's a good question. So basically, because even if you are not using a particular channel set, you still can evaluate the potential cost of using that.
Well, but you would evaluate channel 4 as having no usage.
No, because in that case, what happens is all other channel sets become attractive to go to. So then it becomes the probability thing where you sort of randomly pick one of them and then try to reinforce them. And so,
but I thought you said, you have a problem with that you have to worry about the connectivity constraint then.
no, the connectivity constraint arises when different nodes uses a different set of channels, where if I cannot communicate with you on a channel, my cost to you on that channel is infinity. And that is a the basic element that we take into account in calculating the channel set cost.
Okay, why aren't if everyone is on 1, 2, and 3, why aren't channels?
No, in that case, there is no, the infinity thing is irrelevant. Because when everyone is connected to everyone else, the problem is that the cost of the current channel set will appear to be much greater than the cost of every other possible channel set in that case. So therefore, you sort of randomly pick other channel sets and then try.
I guess somehow there's some, you have some math that you're.
Yeah, I haven't included the details of that.
I think you're trying to say if the neighbor cannot use channel C, the cost is infinite, as opposed to does not use. If you have a perfectly good channel that's underutilized, that channel would be considered attractive. But if you have an unusable channel, that's a channel you would want to stay away from.
That's your guess. That's your guess.
That's a guess. Am I guessing right here?
Is he?
So I didn't quite understand the second.
I'm just curious about the phrasing. If you have a channel that you can use but don't use,
Right.
that channel would be attractive. It's just not
Yeah,
used right now.
exactly. Yeah.
On the other hand, if you have a channel you want to use but can't, its cost is infinite.
Right. I mean, I think that second part I will sort of rephrase by saying that if you were to use that particular channel, but the neighbor.
It's busy, it's noisy, whatever.
Right, and then that for that particular combination, you would have an infinite cost coming in. Okay. So yeah, I avoided the math, and just for clarity, I think it's causing more problems. Sorry. Anyway, so basically that is about how you calculate the goodness of a channel set, and then we have a number of other optimizations to sort of control the amount of exploration you do. This is in relation to the convergence aspect, and also in terms of trying to control the amount of overhead. Like I said, you try to adjust the frequency of these adaptations and also frequency of hello messages being sent out in response to how well you're doing in terms of the channel allocation. So if you are in a virgin state, you're going to do this more frequently, and then if you're pretty much 90% or 100% connected, you're going to reduce the frequency. So that's the high-level idea. Okay. So in terms of the evaluation, we've done this by simulation. Although we've implemented a part of this protocol on our test bed, the full-blown implementation is still happening at the moment. The complete protocol has been evaluated in the quadrant simulator in conjunction with the baseline single channel approach and a negotiation-based protocol, which is by far the most practical protocol that's there in the literature. So it's called the asynchronous distributed coloring, and that protocol was compared as well. And we've done experiments with varying number of nodes, channels, interfaces, all sorts of combinations. But what I'm going to focus on is a specific subcase, mainly corresponding to what is available in terms of channels in Europe. So you have, in the 5 gigahertz, you have about 11 channels, and 3 radios is what you can get with current embedded computer boards for multi-radio platforms. So regarding the other parameters, we've sort of based our choices on past measurement work, and we've used a routing protocol which actually takes into account both intrapath and interpath interference. It has been shown to be better than the well-known ETX, CTT metrics. So this is what we do for the routing. So that's something that sits on top of the channel allocation protocol. Okay, before I sort of show the results, I want to spend a little time on discussing the metrics that we use. So the basic metrics that we use are connectivity and some notion of channel utilization. So for the connectivity, the way we measure this is in comparison with a single channel network. Okay, so here the single channel network has 100% connectivity. So that is basically the idea. And if the multi-channel multi-radio, multi-channel case results in the same connectivity, then we sort of are good. That's what we are aiming for. The higher the better in this case. So if some of the links are not enabled because of poor channel allocation, that we want to avoid and want to capture as part of this metric. The channel utilization essentially tries to measure the extent to which channels are evenly utilized. We want to use all channels more or less equally, so the lower the better. Sort of may not be straightforward to sort of view that always we are seeking better channel utilization by having higher channel utilization, but here lower the better. And the way we measure this is we try to take the difference between the maximum number of interfaces assigned to a channel and the minimum number of interfaces assigned to a channel, and then use that to determine how uneven the channel allocation is. So let me show an example to make this clear. So suppose that you have a 25 node scenario with 2 backhaul interfaces per node and 3 backhaul channels. So imagine that you assign your channel allocation protocol gives you this allocation. So basically, channels 0 is assigned 25 interfaces to the whole network, and channel 1 is assigned just 6, and then channel 2 is assigned 19. Okay. So then here, the way you calculate channel utilization is as the difference between the max and the min. Okay. So basically, it would be 19. And if you look at it as a percentage of with respect to normalization using the maximum network size, which is basically the upper bound for this, then you get 76%. So we are trying to get this lower. So basically, as you can clearly see, this is uneven channel allocation, and that is captured here.
But that is not necessarily bad, right? It depends on the traffic on the channel. It depends on, if I'm fine with 25 being on channel 0, so be it, right? Like, there has to be some other metric other than just the number of channels. Or unless in your simulation you had equal amount of load on all the channels and so on and so forth.
No, so basically we are not doing this in a traffic dependent way. Okay, so basically this is based on purely the number of channels assigned to the number of interfaces. So we do this in a traffic independent way.
Yeah, but the question is, why do you need it to be evenly utilized?
Yeah, it's possible that your algorithm actually, based on the interference, whatever, the neighbor information and all, and the network settled down with this kind of configuration. It looks perfectly fine to me. Like, why should
It's a relative thing when you're trying to do evaluation. You're looking at the existing techniques versus what we are doing. So if we are able to arrive at a more even channel utilization, that is a better thing.
No, but why wouldn't I look at something like system utilization? Right?
A better example is if it's a sparse network,
Right.
then even if there are a lot of them on a single channel, it's not bad. Why is it?
Channel
So if
utilization.
it's very dense, then I can understand spreading it over different frequency is a better solution.
Right.
So even orthogonal to the traffic thing, it depends upon the topology. So I don't know why this metric is good or bad.
Also, using multiple channels has a lot of overheads in your scheme, right? So if everybody can use, well, you do need, if everybody can stay on the same channel, you may as well suspend the procedure and you're fine and you don't have any excess traffic. Let's say you have enough bandwidth. You may as well not worry about what's going on everywhere else. Right?
Yes. So in some ways,
more adaptive.
so
But
one
in some
could.
sense, he's trying to address the connectivity, your notion of these overheads, right? So the fact is you have lots of channels, but if he has good connectivity, then it means there's still whatever channel you transmit a high probability that a big group of people will get his message. Okay. Kind of very confusing. I mean, I agree with you.
I don't fully understand. Yeah, maybe I
So
don't
if one way to take traffic into account and then do channel allocation depending on the nature of the traffic, then your argument is valid.
I'm not even saying the nature of the traffic. I'm saying that there should be some kind of a system throughput kind of a thing. Right? Even if you're doing simulations with, say, topologies, 2-hop topologies, let's say, okay? So why would I look at the number of channels? I would look at the total system throughput and how much better I am.
We
given
do
the
consider
speed.
that as well.
I think the crux of the matter is this, that you answered, I think, Chandru's question earlier. Like he said something like if there's exactly as many radios as channels, well, what then? He said, well, that problem's trivial because you have one radio per channel. But actually, if you create that situation, you just transfer the difficult problem to the the routing layer. And
Yes.
the question is, how do you partition your flows over those
Exactly.
channels, and how do you define routes within channels, and you have now full control of the physical layer. You don't have these constraints, right? But your problem's extremely difficult. This is difficult.
Yeah, but I think this is more the realistic case, because people have looked at that specific scenario that you mentioned, where you only pick subset of the existing channels and then assign all the nodes to the same set of channels. So essentially,
The physical situation that, you build this box with 11 radio cards because there's 11 channels or whatever it is. I mean, it's kind of a no-brainer.
right.
I mean, it's in terms of building hardware, it adds $10 to the cost of the box.
Yeah, I mean, I think, so basically, looking into the future, if that is still a very practical, sensible thing to do, then one could question the significance of what we're trying to do. But as it stands, you do not have this capability. Of course, in some ways, in theory, I agree. In principle, that you could have as many interfaces as the number of channels. Channels could be 1,000 channels in a dynamic spectrum scenario. So basically, if you could have 1,000 interfaces, or you could just use one interface to sort of use all 1,000 channels, then if all of these is practical and realistic, then I think this is completely
I guess my point
complicated
is
way of looking at it.
the underlying core problem of
Right.
how you use all those channels to build a network is still there, even if you have a radio for every channel.
Right.
The real problem isn't any simpler.
Yeah, you still need to pick the right channel and right interface to forward your traffic, and that is taken care by the routing protocol, like in
Well, the
any
point
other
is that with a lot of channels, a lot of radios on those channels, how you should do the routing protocol is a very, very difficult thing.
I mean, I think
And
it
it's
is
hard even when there's one channel, we have a lot of debate, right?
sure. Yeah, I mean, I think here we are primarily focusing on how to arrive at a channel allocation that the routing protocol can.
Even in your situation, okay, so you end up with systems where, you have 3 channels, right? Not clear, maybe it's clear to you how to do the routing in a system context. Is it?
So there are these metrics that have been proposed, which actually have been shown to be quite effective in trying to take into account the channel diversity along a path and across paths. So the metric that I presented, or I didn't go through the details, but it tries to capture intrapath and interpath interference in a multi-radio context. Okay, so there are other people who have looked at this issue, assuming that channel allocation is done for you.
Yeah.
So
Okay.
it's sort of you're decoupling
That's
this.
fair enough.
Sorry.
That's fair enough.
Okay. So these are the 2 metrics that we're looking at, and of course we also looked at throughput, delay, and all these other sorts of metrics as well. So basically, here's a plot which actually shows how over time both ADC and LCAP function. The ADC connectivity is not shown here because it is always connected through the use of common channel. So there's always a common channel shared by all nodes. So connectivity is always 100%. So in our case, as you can see, it sort of converges to 100% connectivity in a short period of time and then stays in that state. And regarding channel utilization, there's a significant difference, an improvement compared to ADC. And this happens because of 2 reasons. One is the overhead of doing communication actually slows down or sort of creates these oscillations with ADC, because it will take longer, because there is a 3-hop negotiation that happens in the ADC protocol, which sort of slows down the channel allocation process in the case of ADC. And in terms of the difference in channel utilization, the use of a common channel in the case of ADC hurts ADC. So it is, yes.
What is 100% connectivity mean?
100% connectivity means that you are as connected as a single channel network. Okay, so if you just have only one radio, one channel case, then you have a certain topology that you get,
Right.
and that's what we are trying to match.
How do you quantify connectivity?
Just like take any two nodes,
Yeah.
so there is always a path from that node to the other node.
Okay.
Isn't it one hop connectivity though?
It's one hop.
It's one hop?
Yeah. So one hop, basically we take the topology that's given in a single channel case, and then we are trying to get that in the multi-channel case as well. Now, of course, there could be argument that you could take the graph theoretic notion of K connectivity. So then there is an issue of the path length. So you could end up having just a tree, which might cause very long paths than what is possible if you are more connected. Okay, so therefore we are not trying to address that issue. So basically we're just trying to maintain what is achievable in a single channel.
When you say the long pass, is that a physical longer propagation pass or just
More number of hops. More number of hops.
So can you explain the graph? ADC, you say channel utilization is 80%. Is that correct? I'm reading?
Yes, yes, yeah.
And LCAP is 50%?
Yeah. So
So you were saying that
the lower is better, like I said before. So lower indicates more even channel utilization. Okay. So here the unevenness comes from the fact that you're using a common channel, and the slowness in the convergence happens because of the negotiation overhead. So you have this 3-hop handshake through distributed mutual exclusion, which is quite slow in practice.
So it starts out as a very well utilized
Yeah,
system,
exactly,
and then
so right.
it goes back.
Which one?
No, it's not.
Yeah, you start off in a random way, partly because there is the connectivity, there is a tension between connectivity and channel utilization. So I can completely disregard connectivity and I can get better channel utilization. So that is something which is very well known. So for people who
So connectivity is the number of links.
right. Yeah. So if your topology is more connected, then there is a greater requirement to reuse channels, because you're limited in the number of interfaces you have, right? So you're limited in the number of interfaces you have, and you want to enable more number of links. So then there is no way you can have the same kind of channel reuse in that scenario compared to the case where you take off certain links in the network. Okay. So there's past work which actually sort of discusses this in a multi-radio context. I can refer you to that. Yes.
Why do you want to channel utilization experiments start at different normalization value?
Two channel.
Why does the render do start at different?
So those connectivity and not.
Oh, one is connectivity and the other is channel utilization. Sorry, so basically.
No, there's no channel utilization. The red bar,
Oh, the red line
and the black line.
Yeah,
Why
so-
is the black line starts at 9% and the red line starts at 40%? Or the utilization?
She's saying why is the percentage normalized value different for the two lines at the beginning of the start?
At the beginning, because they're starting in a random state really. I mean, I think in some ways you pretty much have a random channel allocation that you start with, and then that's basically this is not the right state. So as you can see with the ADC, it is 100% connected and it is trying to improve in terms of channel utilization as time progresses. So you're trying to allocate different channels for your other interfaces. In our case, you're not connected to start with. So you're not connected in the sense that we're seeking, and therefore it sort of increases.
What if you made your starting point for LTAP be like one person, each node has one default channel that they automatically.
No, there is no default channel in our case. So basically what we...
I'm just choosing a starting point for your iteration. I mean, you're defining an iteration, right?
Right.
So I just make it the starting point be, you start with everyone always uses channel 1, and then they randomly choose some other ones.
Right.
And do you start up at 100% connectivity?
Yeah, I think that's a different starting point one could try. I mean, I think we haven't seen the impact of the initial state. And I think that's an interesting thing to look at. So one could start with that very highly connected state and then gradually sort of distribute the interference on more things.
So somehow, is it possible that you would end up converging to some other bar for your LCAP?
Meaning higher or lower than that if you start with a different, yeah, could be. I mean, I don't have an answer to that.
So you didn't try other starting states to see?
So we mainly started with sort of all channels being identical, all nodes having this identical channel allocation, and all nodes having random channel allocations. So what is shown here is random channel allocation. If all nodes start in a common state, we still saw that it eventually converges to the same value.
So for the same physical configuration of nodes, did you get the same repeatable results for different random initializations?
These are averages over multiple runs. I mean, of course, there is no single value that because there is this. It depends on the topology of the network. So
I'm saying if you just have the same topology,
right,
1,000 times in a row with a different random starting channel allocations.
Right. So basically, that's what. What we see is around this value, the convergence happens around this value only. So that's what we notice. So what is shown here is an average of several runs where the deviation around this is small.
I think it's very highly unlikely to get the same value.
Well, values of this is not the values of the actual assignments, but the values of the normalized connectivity. Because for instance, the same configuration of nodes in space and the same number of channels, but you always end up with this algorithm that's like 50%.
No, but I think that for that to happen, I think you need to have a unique solution. So here there is not necessarily a unique solution. Here, what tends to happen is if you cannot improve your metric anymore, you sort of
stay. Question about the scientific validity of this curve.
Right.
Really.
What's that?
I'm sort of asking a kind of question about what exactly is the sort of the scientific validity of the curve? Like to what extent does this kind of whatever averaging you're doing to make this nice smoothing,
right,
sort of bury sort of the reality of the randomness of your machine learning.
Sure. So we've sort of also computed the confidence intervals for this, like 90%.
Yeah. So sort of like that's the kind of answer I was expecting you to.
Oh, okay. So I probably took it.
We did this, and it's like.
Yeah, maybe I didn't get the question. Sorry. So essentially, we've done that calculations as well. So basically, from a statistical point of view, these differences are significant. So that much I can say, where the confidence intervals do not overlap. They are fairly tight for a large number of runs that we've used. Okay. And the benefits in the previous slide result in the throughput and delay gains as shown here. So basically, this is for the link layer throughput and delay. Okay. So here we have LCAP, ADC, and the single channel case. As you can see, as a function of offered load, the single channel expectedly tries to saturate much sooner, and ADC, because it is sort of dedicating one common channel and inefficiently using that, it sort of has much lower throughput compared to what we are getting. And the delay differences are even more significant because of the log scale, as you can see. And partly this happens because you have buffering happening. A lot of the losses actually surface as large delays. Okay. So,
by the time this saturating event starts, your delays are actually going very high, right? Because
yes, yeah. And that's, I mean, if you have smaller buffer sizes, I mean, of course, to some extent one could sort of do a multi-dimensional study where we could sort of look at the impact of the buffer size on the delay versus throughput gains, and I think that's something we haven't done. Yeah.
So I think whatever your buffer size is, it's going to blow up because it's already like the saturation is.
No, if you have a very small buffer size, actually the differences here will be much more significant than here. So the delay will.
So anything with more delay will get dropped. Then you will see.
I mean, I'm saying that even if you have a very large buffer.
So the delay would be large, but throughput would be. If you have a large buffer size, I think states which are going through a lot of delay are still there. They're basically getting transmitted, so that will contribute to the average delay. If you have
So what was the buffer size you had?
I think it's probably about 100 packets. This is something that was just default. I think we didn't really modify that. I'll have to check with my student, but basically it's about 100 packets. And we have looked at the multi-hop performance in terms of random and sort of more internet access kind of traffic patterns. And even here also we see that the benefit is substantial, about 40% in terms of throughput improvement. This differences in terms of random versus gateway. The key difference is that in the gateway case, because the gateway becomes the hotspot where the bottleneck lies, some of the improvements get limited by that as opposed to the channel allocation. Okay. We've looked at the overhead of the protocol in comparison with the other protocols and also as a function of the network size. So in terms of the overhead in comparison with other protocols, single channel and LCAP are fairly similar. The difference is primarily because you have multiple interfaces and you have to send hello messages on the additional interfaces as well. So that is the only difference. Otherwise, much of the overhead here is in terms of periodic hello messages in the single channel case, and we are doing the same pretty much. Whereas in the case of ADC, there is also a negotiation overhead, which actually makes the overhead quite significant. I mean, of course, if you compare this number, there is about 60% more overhead with ADC. If you look at the impact of the network size, as you can see, because the only overhead this protocol has is for neighbor discovery, it pretty much is independent of the network size. Okay, it just stays constant, which sort of is a good thing from a scalability perspective. So in summary, I've presented a learning-based approach to distributed multivariate channel allocation. And, in this framework, you have nodes autonomously determining the channel allocation over time through a learning mechanism. And this is aided by a neighbor discovery mechanism that allows you to discover neighbors even in the absence of common channels. Okay. So, in ongoing work, we are doing several different things. These are few of the important aspects. Adjacent channel interference is an issue to deal with in practice, especially if your channels are either partially overlapping or even adjacent channels. This is something that's been considered in other contexts like cellular networks and such, but in this context, people have reported that this is something which is going to significantly limit the benefits of multi-channel in practice, but they haven't looked at how you can incorporate this into a channel allocation protocol to do intelligent channel allocation. That is something that we're looking at. So if I can